So that's the tricky part, is making sure that when you're animating the bouncing ball, it's principles. It's all principles. There's no fancy rig. There's no fancy geo. All we're working with is principles, and that's good. So we just focus on what's important. Now, we'll have a look at, let's see some of the examples I have here. I think that's, okay, there we go. I think there's some examples. Go inside the bouncing ball folder. This little PDF will explain the assignment. So this is what we're going to do. The only difference with the PDF is in the PDF, it shows that the ball starts off screen. We're actually going to start the ball on screen. It's just too big a distance for this thing to travel through. So we're going to start the ball top left, but in frame. It's going to hit the ground twice, and then it's going to bounce out of screen. So a fairly straightforward assignment. This would be like your storyboard. You would get this with a bunch of arrows. And you'd understand, okay, what's going to happen when this thing bounces out of frame. There's also some little notes here about viewport rendering, which we'll talk about in more detail once we get to the play blasting. There's some images that we can have a look at, some strobe photography. I'm sure everybody's seen this in physics class and the old textbooks, using strobe photography to describe to people how gravity works, how we've observed gravity, and how that results in different kinds of interpretation of motion. And what we're looking at here, right, is basically this shape here. In animation, we call it an arc. But in physics class, what kind of curve do you call this? Does anybody want to make a guess?
Parábola.
Parabola. But luckily, we don't have to break out any, y equals mx plus b or any kind of quadratic equations. We just have to fake it, right? So we have to look at how something moves and be able to fake it. What we need to be able to convince an audience of is that we know how to make something speed up. We need to show how it slows down, and we need to show how it changes direction. So that's why the bouncing ball is so important. It has all those three important components. So what we're looking at here at the freeze frames, you can see all the individual strobes, is we can see where the spacing clusters. So when something slows down, that means that the spacing gets closer and closer. That means every unit of time, right? In this case, it's every position, whatever that unit of time is, right? Maybe a frame. For every frame, you can see the height is getting less and less and less as you get to the top. And then it starts to get bigger and bigger and bigger. And most of the time, what you'll tend to see is kind of symmetry. The way it goes up is the way that it goes down. The only time you'll see a difference is if somebody was to throw a ball up in the air. If you were to throw a ball with a lot of energy, it doesn't mean it's going to come down at the same speed. Right? Gravity is constant. So the way things accelerate down is usually something that's a very familiar pattern. But what makes it different is the way it can be hit up. So that can give you a little bit of contrast. But here, where something is just hitting the ground and bouncing up, it's gravity at work. The only thing that's acting on this is gravity, right? So it's very symmetric, the spacing. So it's a very evenly shaped parabola. When we look at the distance going horizontally, you can also notice it's kind of even. So the distance that I travel from here to here, right, is very similar to this distance here, right? So that's the horizontal speed. That's not changing very much. What's changing the most is the vertical speed, right? So I slow up, right? Slow down as I go up, and I speed up as I go down. So the spacing is bigger before I hit the ground, and it's bigger the moment I leave the ground. As soon as I leave the ground, the spacing gets less and less and less and less. Okay, so that's the two patterns, okay? Increasing spacing or decreasing spacing. And then we have an abrupt change in direction. The reference that I have, let's open that up. Okay, so just, again, very easy thing to do if you've got any kind of sports ball that you can grab and just shoot video of. And it's very easy to see. What you'll see a lot of times in video, because our frame rate is not great, a lot of times you won't catch the moment of impact. Sometimes you'll catch just the frame before and after. So you see here, it appears like the ball doesn't even hit the ground. It kind of just drifts, right? So there's a lot of blur that's happening. Sometimes compression happens and you drop frames. But what's really important is to look at the really abrupt change in direction, that big speed change. The other thing that we'll look at is squash and stretch. That's a tool to make things feel more flexible. It's also a cheat for motion blur, right? When you make a drawing, everything is crystal clear. But if you blur that drawing or you smear it or you stretch it, it mimics like what we see in photography. If something moves really quickly and the exposure of the camera isn't going to catch it crystal clear, we get a blur. So that's one tool we can use to kind of create the illusion of speed, right? Is distortion. Okay. But when we look at how things squash and stretch, we always have to think about the volume. Think of it like a water balloon, right? So it's a volume. So that means that the amount that I push down has to push out. It has to feel like the same volume of stuff. It can't just all of a sudden grow really big. Otherwise, it feels like it's a different ball, right? So there's a range you can push things, but you go too far, it sort of breaks believability, which can be great for a certain style. But if you're trying to make people believe what you're doing, it may not be the best choice. Now, this is the squash and stretch I was talking about. The ball hits the ground, I'm squashing the ball, and I stretch it just for one frame, right? So I go from squashed, stretch, then I go back to a circle. This is an important part of squash and stretch, is that it's usually done over a very small number of frames. We want the audience to feel squash and stretch, not necessarily see it. Otherwise, the object starts to feel, again, like it's made of silly putty, that it doesn't have any structure, right? It doesn't have any anatomy. So when we're looking at this, right, this is the classic formula for a bouncing ball. The spacing is clustered really tight at the top. It barely moves. And then the biggest spacing happens just before you hit the ground. So that's when you're going fastest. The moment just before you hit the ground is the fastest you're ever going to go. So that's the biggest distance. Okay. Then we rock it back up, and the same thing. The spacing gets closer and closer and closer and closer and closer. Okay. So that's the squash and stretch with a cartoony bouncing ball. Now, if I throw on a penny, okay, and do the same thing, what happens to your perception of the squash and stretch? Does it look like it's a good idea for the penny?
Not really.
No, right? So this is a big shift, right? Pixar, when they were working on their first films, that was one of their laws, right? So they gave to everybody, is like the first rule is truth to materials. So you can see I run into a little bit of a problem here. Well, if I've got my formula for a 2D ball and I put it on an object that has more complex textures and lighting, it's not going to work. So I got to fudge the formula a little bit. So if I just look at this and say, well, what happens if I just get rid of the squash and stretch? This is what happens, is the frames that I'm using to do the squash and stretch, what do I do with them? If I just throw them away, what happens is the penny sticks, right? So now it sticks to the ground. So it shows the difference in timing, right? So with squash and stretch, I'm using frames at the bottom, right, to do the squash and stretch. If I'm not going to do that, what do I do with the penny? How do I fix that? So if I keep the timing exactly the same, the only other variable is the spacing. So if each object, it's still 1 second to go down and come back up, 12 frames to go down, 12 frames to come back up, that's my time, then the only thing I've got left is spacing. So they're going to move slightly differently. Oh, sorry, where's the corrected? There we go. So they hit the high point at exactly the same time, right? They don't hit the ground at exactly the same time, but they both reach the high point and cycle back the same frame. So what I had to adjust was the spacing. So I had to keep the penny more tightly spaced, right, as it falls, because the rubber ball, the cartoony ball, has to get there sooner because I need the frames for the squash and stretch. So it has to fall faster so I can use that time. The penny, I'm just having it hit the ground 1 frame and ricochet up. So it has fewer frames to fall and go back up. So it spends more time in the air. Okay, same timing, different spacing. Okay. Now I wanted to load up what our assignment could look like. Now, the only thing that's different with this example is not possible. This is a ball that doesn't lose any energy. So we're not going to do that. We're going to have a ball that bounces, and each bounce gets less and less as it goes across the screen. But that's essentially what we're doing, the ball bouncing across the screen. And if you look back in course materials, we can go to this sheet here. And this is how we're going to go from the concept, what we're going to do. How do you plan things out? So the plan for the assignment is, once you know what the action is, what's in the storyboard, right? The storyboard might be timed for you in an animatic, so that will give you a rough guide as to how long the shot could be. But a lot of that job comes to the animator. So you're told, got a ball starting top left, it's got to hit the ground once, go up, hit the ground again, and then go off screen. We need to start putting some numbers down. But the first thing we usually identify are the key positions. And usually when we're talking about anything that's bouncing or jumping or moving around, and a simple place to look for a key, a really important position, is a high point and a contact point. So we know that this object is in the air and then it's going to hit the ground. So those are 2 keys. So I know that they're going to happen. The real question is when. So the first thing I'll do is the timing, and I'll start with a guess. So again, that's where a metronome or a little bit of, if you've played music or gone to dance class, that'll help you kind of get that internal metronome. And I always start with simple guesses. So if I was to have the ball bounce with like 1 second, boing, boing, it's really slow, right? So 1, 2, that feels way too slow. So if I go to like 1 and 2 and 3 and 4, okay, that's half time, right? So that's half measure. That's 12 frames. If I was to do thirds, right, that would be like cha cha cha, right? 1, 2, 3, cha cha cha, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That would give me an idea of how quick that would feel. So you could use a stopwatch, a metronome, right? But the easiest thing to do is look at video and look at reference. But I start with easy fractions of 24. I start with a second. That's too long. Let's try half a second. That's 1 and 2. Then I'll start with, well, what about a third of a second? What would that be? So I know half a second is 12. A third of a second is 8. A quarter of a second is 6. So those are the big numbers that I start with, just because I can relate that to something like a metronome, like a musical beat. And then I'll make variations. And there's nothing magic about those numbers. They're just easy guesses. And I've been doing this a long time. I will never worry about getting the timing correct the first pass. I have to get something down first. And the only way I'll know if it works is when I hit the play button on the video. That's the only thing I can trust. Everything I'm doing is a guess. If I don't like it, I will adjust it. If it's too slow, cut the frames, right? So if it's too slow, take away frames. If it's too fast, add frames. But we'll start with the big guesses. So the first guess I made, let's just do half a second. So I start at frame 1, and at frame 12, I'm going to hit the ground. Or sorry, frame 13, I'm going to hit the ground. 1 plus 12 gives 13. That gives me the timing, the when. So ball up here, hit the ground. And then the next bounce, well, I'm losing energy. I'm not going as high. So if this distance from here to here, that height, if that's half a second, that's 12 frames, and this is a smaller distance, it shouldn't take the same amount of time. If I use 12 frames to go up here, it's going to feel slow because I'm not going back up to the same height. It's going to feel a little bit floaty. It's going to feel like, why am I taking so much time to travel a shorter distance? It's going to feel slow. And then it might not feel like it's bound by gravity anymore. So I know that it has to take less time. So I'm starting with the simple fractions. Half a second, 12. Then I did a third of a second, it's 8. So that gives me 13 plus 8 gives me the 21 plus 8 gives me the 29. And then I made another guess here, 4 frames. I know this guess is not right. I've done this demo enough that I know this isn't going to work, but we'll start with the guess and you'll see why it doesn't work. And then we'll have to probably add frames here. It's too quick, but I need to have this thing hit and then bounce out of shot. And I made a guess, 4 frames, 1/6 of a second. And just, oh, sorry, 1/4 of a second. No, yeah, 4 frames, 1/6 of a second. That's very, very quick. 4 frames is really quick. It's hard to see 4 frames, right? It just goes by really fast. So now that we know when things are happening, once you have the keys blocked in, the next step is to look at how. And that's where I drew this little timing chart. This is something that we'd used in 2D animation to block in the spacing, figure out how something is going to move. So the way that you work with the chart, there's frame 1, and there's frame 13. So that's my keys. So you show the system, okay, this is where you're starting, this is where you're going. Frame 11, I want that to be halfway in terms of height from 1 to 13. Why is that? Well, this is the biggest distance. The biggest distance happens before you hit the ground. So an easy distance to measure is half. So what I'm doing is I'm basically going backwards, right? So I'm at 13, I go 2 frames back, go up and say, okay, that's going to be halfway. Excellent. Then what I'll do is I'll work backwards again, and I'll cut that distance in half. And I'll keep cutting that distance in half and half and half, going backwards, because I'd rather start with big distances to measure those than really tiny distances. If I start working over at frame 1 and try and guess how much I should move this thing, the problem is if I get it wrong, everything else relates to that. So a little distance is hard to measure and hard to guess right, but a big distance you can feel more confident with. A big distance like a half, and again, it's just a rule. This is not physics, right? A physics teacher would throw me out of the classroom and say, you're insane. But it does create a pattern that feels like an acceleration. It works. So this is how we're going to start the demo. We'll start by building the keys, then we'll start adjusting the spacing, and I'm going to show you 2 ways to do the animation. One where you do almost all the work yourself, and another way where you're using the computer to help you. And the most important thing is to figure out where the computer's good at helping you and where it isn't very good at helping you. So you figure out where you have to put most of the effort.